Hi, Chem 101 students. So now we're here for the third and final lecture for transition metal complexes. This is where we're going to talk about all about color and the theory behind why these transition metal complexes produce pretty colorful solutions when other things don't. And noticeably, why some transition metals do not produce colorful solutions. So for example, here, these are all transition metals that are in water. So their ligands, because they're in water, their ligands are all water. And you can see, depending on the transition metal and its charge, you'll have different colors here. So this is cobalt 2, which makes a red solution in water. This is nickel 2, which makes a green solution in water. Copper 2 makes a blue solution in water. And zinc 2 plus does not have any color. Interesting. Is there an explanation for why this is? Yes, there is. So we can have different colors if we have the same ligand here, which is all water, but different transition metals as a part of the complex. We can also have different colors if we have the same transition metal, but different ligands. If we have the nickel here with water ligands, it will make this nice turquoise color. If we have nickel 2 here with amine ligands, it makes this bluish color. If we have nickel with ethylene diamine ligands, instead it makes this purple color. So what's the deal with these colors? Okay, the colors will differ if we have different metals or if we have different ligands. Well, what's going on here? When you observe a solution with a color, what's happening is that there's going to be electrons in a lower ground state. And those electrons, in those atoms, when they encounter light, if the difference between the energy of one position for the electron, the energy of another, exists and that energy difference is the same as that for visible light, it will absorb some visible light. And this electron will absorb that light and move up into an excited state. And so that light that is absorbed is not the light that you see, it's actually the light that isn't absorbed here. And so the energy difference between these two levels will be h nu. And just reminding you here of some old formulas and some constants here. Of course, you'll be given the constants here. H in this context stands for the Planck's constant 6.626 times 10 to the minus 34 joules times seconds here. C stands for the speed of light, 3.00 times 10 to the 8th meters per second. Okay, and energy, as it says here, equals Planck's constant times the frequency. And the speed of light equals the frequency of the light times its wavelength here. And so these are the relationships that you'll need to know to be able to solve for the energy of a particular light given its wavelength or its frequency. If we combine these, so if we divide here both sides by wavelength, then the wavelength cancels and we get that frequency equals c over the wavelength here. And so plugging that in right here for the frequency, we get that the energy is h times c over lambda. So if you've got the wavelength, you can determine the energy. Make sure that your wavelength is in meters. For this to work, notice that the speed of light is in meters per second. So if you're going to use this, wavelength must be in meters for this to work, okay? And of course, frequency here must be in frequency is going to be units of 1 over seconds, because here speed of light is in seconds, so units must be 1 over seconds. So this solution will appear violet, or this one here appears let's see, yeah. And so this is an absorption spectrum here. So this is telling you, based on the wavelength, what light is absorbed. So, and here's the color of that light. So the light that's absorbed is mostly like blue light, green light, and yellow light. What isn't absorbed is red light and violet light. And so because the violet light is not absorbed, what we see is like a violet color. And those colors are transmitted. So be very careful when you're noting what light is absorbed. That is not the light you see. What you actually see is the complementary color. So useful for this is the color wheel. So for example here, if we have a transition metal complex that absorbs very strongly around 720 nanometers, like right in here in the red, then that means that the solution is going to appear green. If it absorbs most strongly in the red, it's going to be absorbing all around here, so it's going to leave the green color mostly untouched, and so it'll appear green. So the way you determine what color a solution looks like is if you determine that it absorbs very strongly red light, its color will be green, or if it absorbs very strongly yellow light, then its color will be violet. The color will be the complementary color. You don't have to memorize this color wheel. I'll always provide it to you when you need it, or you can, look back. It's useful to have for these questions. Okay, so now what we're going to do is we're going to use a couple of different types of bonding theories to try to explain to us several properties of these transition metal complexes, their colors, but also their magnetic properties. So in terms of bonding, one way to describe the way in which transition metals bond to their ligands is in terms of valence bond theory. So valence bond theory says that when two atoms bond, they bond because of an overlap in their atomic orbitals. And so we have a metal here which has a vacant atomic orbital, and we have a ligand that has a completely occupied atomic orbital with two lone pairs. And so when those atomic orbitals overlap, they overlap and share two electrons, and they make what's known as a coordinate covalent bond. This is called a coordinate covalent bond because unlike normal covalent bonds where each atom gives one electron to the bond, in coordinate covalent bonds, both electrons come from one atom, which in this case is the ligand donor atom. Now, in terms of bonding, there's several different shapes that can result from the bonding. One of them is a octahedral shape, as we've seen before. This will have 6 bonding orbitals all 90 degrees away from one another. So if we have a compound that has a coordination number of 6, it will have bonding arrangements in this fashion, 6 bonding orbitals here, all 90 degrees from one another. If we have a square planar complex, it's because it's going to be 4 orbitals that are used for bonding, positioned in a flat arrangement 90 degrees from one another. Now, which compounds are going to bond in which way? So what you saw here are equivalent bonding orbitals here. So these are hybridized bonding orbitals, and that's the central crux of this valence bond theory, is that when the bonding happens, you get identical bonding orbitals. So in an octahedral arrangement like this, you've got 6 identical bonding orbitals. Here in this square planar arrangement, you've got 4 identical bonding orbitals in a square planar arrangement. And in terms of hybridization, so up to here, linear and tetrahedral, this should be familiar to you from your Chem 150. If it's linear bonding, you need 2 orbitals. So those orbitals will be hybrid orbitals made from an s and a p orbital. So we call those sp hybridized orbitals. This will be the case for all compounds that have coordination number 2. Now for compounds that have coordination number 4, the hybridization can lead you to orbitals in 2 different shapes. If the hybridization is sp3, using 1 s orbital and 3 p orbitals hybridized to produce 4 bonding orbitals, you'll have a tetrahedral geometry. However, if the hybridization involves 1 d orbital, 1 s orbital, and 2 p orbitals, referred to as dsp2, that will result in a square planar type geometry. This happens to be an example of a compound that will do this. I'll explain why in a moment. And then finally, for compounds with coordination number of 6, these can bond with two different hybridizations. One is called D2sp3, and the other is called sp3d2. And the difference between them has to do with what energy level the d orbitals that are involved in the hybridization come from. If they come from the lower energy orbital, d orbital, it will be called D2sp3 hybridization. If they come from the higher energy orbital, this will be called sp3d2 hybridization. So let's take a look here at the ion cobalt 2+, which has the electron configuration argon, 3d like this, 3d7. 4s is empty, and here's why. Let's look at what it would be for a neutral cobalt atom. Going back to our periodic table here. So for a neutral cobalt atom, our electron configuration would be, cobalt's right here, so it would be argon, and then it would be 4s2, and then it would be 3d, 1, 2, 3, 4, 5, 6, 7, 3d7. But, so this is for cobalt. But if we have a cobalt +2 ion, then this is going to lose the s electrons. Two electrons are going to come from the s, so it's going to be just cobalt 3d7. So there'll be 7 electrons in the 5 orbitals that are the 3d orbitals. And so going back to the slides here, this is representing those 5 orbitals. There's 7 electrons, 2 of them are paired up. Okay. So now when the hybridization happens, so we're going to show here what happens when it's making a tetrahedral complex. So here, the hybridization is going to be, what happened? My cat keeps pulling on my mouse. So the hybridization can, this is for this, we're going to do for this cobalt complex right here. So this hybridization is sp3. Now, how would you know if it's going to be sp3? That's a big question. How will you know if it's going to be sp3 or dsp2? I'm going to have some way of telling you. So I'll either tell you outright that it's tetrahedral or square planar, or I'll tell it to you based on the isomerization. That's one way I like to do it. Like this one has cis-trans isomers, right? Which can only happen for square planar. So that's another way that I could tell you. But the way the hybridization happens is that it's sp3, which means that the hybridization is going to involve combining this 4s orbital with the 4p orbitals. All of them are empty. Now the orbitals have to be empty because it's going to be the ligands that provide the electrons. So these are all the electrons from the cobalt. These 8 electrons are being provided from the 4 chloroligands, 2 from one ligand, 2 from another, 2 from another, 2 from another, for a total of 8. And then these all combine and they make 4 sp3 orbitals. So when the hybridization happens, these are now all called sp3, and they have 8 electrons. But what was used to make them was the empty 4s orbital and 4p orbital. And that's tetrahedral sp3 hybridization. Now what about this compound right here? Now this one, we have said, undergoes dsp2 hybridization. And this happens to happen a lot for what are known as D8 complexes. So nickel is a D8 complex. It's called a D8 complex because there are 3 electrons in the 3d orbitals. If we go back, we can see why this is the case. So cobalt had the cobalt 2+ had the electron configuration argon 3d7. Nickel 2+ would have the electron configuration argon 3d8. So it's a D8 complex. That's one, or D8 ion. That's what we would generally call it. And the complex will be D8. So something that will happen a lot of times with D8 is that this electron here will move and pair itself up with this one. So you end up with this, and it's out of here like that. And so this frees up this d orbital for hybridization. So at this point, this d orbital will be empty, and so it can hybridize one d orbital, one s orbital, and two p orbitals. So these are going to be now the ones that are hybridizing. And so, whoops. And that's what we see right here. So remember, the red electrons are coming from the ligands here. So these are the 8 electrons that were originally in the nickel, the tetracyanonickel 2 complex. But now these are all in the remaining d orbitals. One d orbital has been hybridized along with one s and 4 p. And so these D8 complexes tend to make this DsP2 hybridization, which results in a square planar geometry. So these are the 4 orbitals, and again, these red electrons come from the 4 ligands, 2 from each one. Now, when it comes to producing the complexes, sometimes there's more than one way in which the hybridization can go. This is true for cobalt 3+. So we saw cobalt 2+, which had 7 d electrons. Cobalt 3+ has one less, so it has 6 d electrons. So at this point, it's possible actually for, it may or may not happen, but it could happen that this electron goes and pairs up with this one, and this electron goes and pairs up with this one. Okay, and then we end up with 2 empty d orbitals. So we could end up with D2 sp3 hybridization, or the other option is sp3 d2 hybridization with the higher energy d orbital. And so if the higher energy d orbital is used, and so here is this one that I outlined in blue, and again, there are 6 ligands now, 6 ligands, COF6. We can get the what's known as the high spin complex here, which involves the hybridization of the higher energy D2 orbitals. And so this would be sp3d2 hybridization. And again, there are 6 ligands, so those provide the 6 pairs of electrons in red. 1, 2, 3, 4, 5, 6. And after the hybridization happens, these are all new orbitals. They're no longer s and p and d orbitals. They're hybridized orbitals. Or the other option is that we can take, as I said here, the red option is we can take these lower energy d orbitals and have d2 sp3 hybridization. This is what happens if it's a cyanoligand, 6 cyanoligans. Again, there are 6 cyanoligans, each provides 2 electrons, 2, 4, 6, 8, 10, 12 electrons total, 6 pairs. So this can occur via a high spin or a low spin complex. Now, the one problem with valence bond theory is, number one, it doesn't tell us anything about the colors, which is a weakness of valence bond theory in this respect. The other thing it doesn't tell us is why a complex might be high spin, like the COF6, or why it might be low spin, like the hexacyano-cobalt 3 here. Cobaltate 3 rather, since it's negative. So this doesn't tell you why compounds would be high spin or low spin. So, and it doesn't tell you why they have colors. So we're going to have to rely on a different theory to explain the colors and the high spin, low spin thing. That theory is going to be crystal field theory. So this crystal field theory takes into account that there is an electrostatic interactions between the incoming ligands and the orbitals in the transition metal ion. And this changes the energies of the various d orbitals that are in the metal ion. And the result is that there is a splitting in energy, and so not all the d orbitals have all the same energy. And this is a very good way to explain why transition metal complexes have colors, whereas many others don't. It has everything to do with the d orbitals and this splitting of energy that we're going to observe along with crystal field theory for these d orbitals. So when we have a complex here, this is a diagram showing for an octahedral complex. Now the pink lobes and the blue lobes, these represent the d atomic orbitals of the transition metal ion. And so these are the shapes of the d orbitals. Most of them are just cloverleaf shape, with one of them being this funny toroidal shape in the middle with two lobes. And so these lobes indicate that where the electrons are most likely to be found in the d orbitals in the transition metal atom. The ligands show the places where the negative ions here, these green spheres, represent the places where the ligands attach to the transition metal ion. And so they're attaching, in the octahedral arrangement, one on each side, all 90 degrees from one another. And for 3 of these possible atomic orbitals, the ligands approach in a way that is quite far away from the orbitals. And so there's less of a repulsion between the electrons in the orbitals and the electrons in the ligands. And so these end up being lower energy d orbitals upon the formation of the complex. Whereas 2 of the ligands here have a heavy, or 2 of the orbitals have a heavy overlap with the positions of where the ligands are. So there's a greater repulsion between the electrons in the ligands and the electrons in the orbitals. So that produces 2 higher energy d orbitals when you have an octahedral complex. And so what you get is what's known as the crystal field splitting. So in a free transition metal ion, all of the d orbitals are degenerate, meaning they all have the same exact energy. However, when the ligands begin to approach for bonding, you get a split in the energy, where those 3 orbitals where the ligands are far away from the orbitals, those stay lower in energy. They're still higher in energy than the free metal ion because there is some repulsion between the ligands and those electrons in those orbitals. But the energy is higher for those orbitals where there's a strong overlap between the position of the ligands and the position of the orbitals. And so we get this crystal field splitting. And the reason why we observe colors in transition metal compounds is due to these d orbitals in the crystal field splitting. This energy difference is generally right in the visible range. And so the result is that because we have this crystal field splitting, that's why we get all these pretty visible colors for transition metal complexes. And this is why they're used in paints and in art and all of that, because they provide us with these very colorful complexes. Okay, so in terms of what's going on here for this crystal field splitting, as I said, this energy difference here is in the visible range generally. So here's an example of the octahedral complex titanium, hexaaqua titanium 3. So titanium 3 plus has a electron configuration of argon 3d1. You can see it right here if we go back to the periodic table. So for titanium, the atom, it would be argon 4s2 right here, and then 3d2 1 oops 1 2 4s2 3d2. But for titanium 3 plus, the 4s electrons will be removed, and then one of the 3d electrons. So it has 1 electron in the 3d orbital, and that's what's being pictured right here, the 1 electron. And when it absorbs light, because this energy difference corresponds to the energy of visible light, it absorbs visible light, promoting the electron to the higher energy level out of the split d orbitals. And so that is why we observe color. Now, that energy difference will depend on which ligand there are. So some ligands, such as ethylene diamine, produce a greater splitting in energy, a larger splitting in energy than do other ligands like aqua. And so if we have an aqua ligand, we end up with an energy difference that results in absorbing the color that is complementary to green. So green is not absorbed, it's what's transmitted. And so the complementary color to green, which is red, here red is absorbed, and green is transmitted, so this appears green here. For the hexaamine nickel 2 complex, the crystal field splitting is larger, and a different color is absorbed, and blue is transmitted. And for ethylene diamine, the crystal field splitting is yet larger, and so we have a different color being absorbed, and violet is transmitted. And so we can see that the crystal field theory and this splitting of the energy of the d orbitals gives us a very good explanation for why these complexes are colorful. So in order to evaluate what color these compounds might have, clearly it depends on what ligand we've got here. We need to determine the impact that these ligands have on the splitting, and this is specified by the so-called spectrochemical series, which is an important thing to have in your notes for these problems. Okay, it'll be quite useful to you. And so for these are ordered in from one end the weak field ligands, the weakest field ligands, to on the other end the strongest field ligands. And weak field versus strong field is telling you basically when this ligand attaches to a transition metal, what impact does it have on the splitting? How big is the splitting due to the presence of that ligand? And so with the aqua ligand, aqua is around in the middle here, and so this results in a smaller splitting, a smaller energy difference between these d orbitals, versus the amine ligand, which has a larger crystal field splitting, we can see here, which is less here than ethylene diamine, which has an even larger crystal field splitting. And we can use this spectrochemical series to evaluate the relative crystal field splitting of these various complexes. So this also takes into account not only the color properties, but the magnetic properties of low spin and high spin. So previously we had used valence bond theory to show the hybridization in a high spin complex versus a low spin complex, but we did not have any explanation for why they were high spin or low spin. And crystal field splitting theory gives you a great explanation for why they are low spin and why they are high spin. So because the fluoroligand is a weak field ligand, these electrons can very easily pop up into the higher energy orbitals. So this cobalt has 6 electrons, as we were talking about before. So the way we would fill them in is like this. The first ones will go in the lower energy orbitals. And because there's a small energy difference here, the next couple will go right here. Then the last one will go down here. So that's a total of 6. And the result is that this can explain the magnetic properties. This is paramagnetic because it has unpaired electrons in it. So this compound would exhibit magnetic properties. However, the cyanoligand is a very strong field ligand, so it produces a very large crystal field energy difference. So if we're filling in the same 6 electrons, the first one would go here, the second one would go here, the third one would go here, but after that, this energy difference is too high for these electrons to go up. The repulsion between them is not larger than the energy difference to go all the way up here. So they'd rather just pair up, and so they do. So the next one goes here, 5th one goes here, 6th one goes here. And so this is diamagnetic. No unpaired electrons. And so that is another big advantage of crystal field theory, is it explains to us why a compound is low spin, and in this case diamagnetic because it has no unpaired electrons, or it's high spin. And this one happens to have unpaired electrons as its high spin. So crystal field theory has huge advantages over valence bond theory. Valence bond theory is very nice for explaining to us the geometries, but it's not very good at explaining to us the colors or the magnetic properties. So these two theories kind of complement each other, even though they're not completely consistent with one another. Crystal field theory is also much more difficult, and it's newer because it has a much greater quantum mechanics and calculation emphasis to it to calculate these energy differences. Now, for tetrahedral and square planar complexes, there is also splitting. The splitting is different than octahedral complexes. So for tetrahedral complexes, 2 of the d orbitals will have a lower energy compared to the other 3. So it's like the octahedral one, but flipped. And then in square planar complexes, what you get is 2 orbitals that are lowest in energy, another orbital that's higher in energy, another orbital that's higher in energy, and one that's even higher than that. And so this is the splitting that occurs in tetrahedral and square planar complexes. So let's take a look at how we might use this, or what question might be asked that is related to this. How many unpaired electrons would you expect from iron in the octahedral complex FeCN6? And so, of course, there's some vagueness to this question, right? We're going to have to, think about, is this a weak field or a strong field ligand? Even then, that is all relative. But if we choose the strongest field ligand, then we're probably going to end up with a low spin complex, most likely. Usually what I'll have you do is compare one to another. So one's low spin, one's high spin, which one is which, based on, which are the ligands here. But first we're going to have to figure out how many electrons there are. So first we got to figure out what's the charge on this iron ion. So we do know that so overall the ion has a -4 charge, and cyanide ions, they have -1 charge, right? Cyanide. So we've got whatever the iron here is plus 6 times the cyanide, which is -1, and that equals -4. So we got iron minus 6 equals -4. So we add 6 to both sides, we get the iron is +2 here. So now we want to figure out the electron configuration for the iron. So for the neutral metal atom iron, and then finally for the iron 2+. So for the neutral iron here, it's going to be so we'll have for Fe, it's going to be iron's right here. And so its noble gas that's right above is argon. And so we're going to do brackets argon. And then we're going to do 4s2 here. 4s2. And then 3d, 1, 2, 3, 4, 5, 6. 3d6. So argon 4s2, 3d6. Now we're doing iron 2+, so it's going to be the 2s electrons that are lost, so its electron configuration will be iron 3d6 here. Argon 3d6 rather. So there's going to be 6d electrons, and that's what we really want to know. Now this is octahedral, so the splitting is going to be like this, 3 lower energy orbitals, and this is going to be a big delta because Cn is a strong field ligand. So that means this energy difference is going to be really, really big. I'm going to put the other 2 way up here. And so what that means is that when we put in these 6 electrons right here into the d orbitals, those are going to end up filling, this is going to end up being low spin here, basically. It's going to be low spin because the difference in energy is too huge for the electrons to overcome without first filling in the lower energy orbitals. So we're going to put in our electrons like this, 1, 2, 3, and then because this energy difference is so huge, 4, 5, 6. So the answer is that we have 0 unpaired electrons in this octahedral complex. Hexacyano iron 2 ion. And so that's the kind of question that you can answer using the valence bond theory. And that's it for our theories of these complex ions. So I encourage you to do the homework this week. So the homework is on its own worksheet this week. It's partially out of the book, partially stuff I wrote. I don't think all the book problems are really great, so I write some of my own for these ones. But you know, start on the homework. Let me know how it goes. Let me know if you get stuck. And I'll see you in office hours this week or in lab or whatever. And I hope you guys have a good week, and I'll see you later.